This is part 2 of the lectures on techniques that are used to calculate electric potential. Specifically in this case, however, we'll look to see what happens when you cannot use Gauss's law in order to calculate the electric field. This would be due to, for example, an asymmetrical charge distribution of some sort, or it could be due to some of the geometries of charge that we saw back in chapter 21 when calculating Coulomb's law, for example, such as the ring of charge. We'll specifically look at the ring of charge here as a problem. However, prior to doing so, I have to lead you through the basic technique that we use to calculate potential for situations such as the ring of charge. We do so by beginning with our point charge calculation, but for a series of point charges. So recall that for a series of point charges, the potential at some point P in space is described by the following expression. Okay, so for a series of point charges, recall that the potential at point P is governed by the following summation expression. And then, of course, in prior lectures, we use this expression like with a dipole and so on and so forth. What we do is we adapt this expression now for a continuous distribution of charge. This then ultimately turns the summation symbol into an integral sign. So here's then how we go about describing that. Okay, so now for a distribution of charge, okay, let me go ahead and draw here a three-dimensional diagram. Like so. And then we have some sort of asymmetrical charge distribution like this. And then let's say that right here is some point P in space. And then therefore we now take a look at an infinitesimally small amount of charge within this overall charge distribution. So right here is a little dq. Its position relative to the origin on the diagram using the vector notation of chapter 21 is r prime. Okay, then here's our point P in space. So then therefore right here is its position vector, that's small r, once again using the notation from chapter 21. And then the last vector on this diagram is capital R like so, which goes from the little dq to point P in space. What we need is we need the magnitude of that vector. We're going to replace the little r sub I here with capital R's magnitude using the notation that we've already seen from chapter 21. So then therefore, potential at point P is the following integral. And then setting up and evaluating this integral for asymmetrical charge distributions or problems such as we saw with the ring of charge is actually fairly easy to do. This integral is usually easier to evaluate than the integral that is necessary to find the electric field using Coulomb's law, for example, like we saw back in chapter 21. Okay, so let me erase the board here. And by the way, this is all assuming that the potential at infinity is equal to 0. And now we specifically take a look at techniques in calculating electric potential when Gauss's law cannot be used. Okay, so specifically we have the ring of charge problem. I have it stated as a problem. Please copy it down into your notes. Okay, so techniques to find electric potential. Gauss's law cannot be used. A ring of charge of uniform linear charge density has a charge capital Q and a radius A. Find the potential at a point a distance z away from the ring along an axis that is passing through the geometrical center of the ring and perpendicular to the ring itself. So it basically just looks like this. All right, so here's three-dimensional space. Okay, and then right here is our ring in the xy plane like so. Okay, right here is point P in space. Okay, the ring has a total charge Q, it has a radius A, and it does have a linear charge density lambda that is uniform. Okay, now let's go ahead and build this integral. And in order to do so, we take a look at a little dq first. So right here is the little dq, and then right here is its position vector, r prime. Okay, that position vector's magnitude, however, is just a, the radius of the ring. Okay, then right here is the little r vector, like so. The magnitude of it is just the distance z that we are away from the plane here where the ring is situated. And then lastly is capital R. Right here is the capital R vector. However, the only thing that we need is its magnitude. We can find its magnitude, of course, by using Pythagorean theorem, because it's just the hypotenuse here of this right triangle. So that then gives us this. Like so. Okay, and then lastly, we need the dq. So this is where the linear charge density comes into play. So linear charge density is charge per length. So the charge is equal to the density times the length. Recall that this is an arc length here on the diagram. That's this distance right here. And that arc length is equal to the radius of the ring A multiplied by the infinitesimally small angle d theta, as we've already seen in situations like this. Okay, so I have everything that I need here for the calculation, and now we just plug it all into the interval. Okay, so the potential at point P is now equal to the following. First of all, dq, so lambda A d theta, and then divided by 4 pi epsilon naught times capital R's magnitude. Z squared plus A squared to the 1/2 power. Notice the variable that we're integrating over is just the angle theta. So then therefore we're going to go all the way around the ring from 0 to 2 pi. Everything in the integral, you'll notice, is a constant. So then therefore it's essentially just constants times the integral of 0 to 2 pi d theta. The integral of 0 to 2 pi d theta, of course, is just 2 pi. So then therefore you actually end up here with a really easy integral to evaluate. So now let's write it out. So 2 pi times lambda times A, and then divided by 4 pi epsilon naught times z squared plus A squared to the 1/2 power, and now we'll start to simplify. Okay, when we simplify, let's get rid of the linear charge density lambda. We'll write that in terms of the total charge which was given and the radius A. So density is charge over length, where length here is the circumference of the ring, 2 pi A. Let's go ahead and substitute that into here. Okay, so the potential at point P then therefore is the following. So first of all, we have 2 pi and then times lambda. So Q over 2 pi A, and then times A divided by 4 pi epsilon naught. And then we also have in the denominator this expression here. I'll clean this expression up for us in just a moment. Like so. Okay, a bunch of stuff, as you can see, cancels. So 2 pi, A cancels like so. And then therefore the potential at point P is the following. Q divided by 4 pi epsilon naught, and then multiplied by z squared plus A squared to the 1/2 power. So you actually end up with an easy integral to evaluate, resulting in the following expression. However, now take a look at the bottom of the problem as it's posted. Let me go ahead and show it on my screen for myself. Okay, the last portion of the problem says, use the calculated potential to find the electric field at point P. Okay, now how would we do that using this expression? Well, let me do some erasing. And now let's take a look at the following general expression that describes difference in electric potential. Like so. Let's go ahead and write the potential difference here just generically as a delta V. Like so. Okay, now let's get rid of the integral sign. We'll do so by talking about the infinitesimal change in potential, dV. Like so. Okay, now on the right-hand side of the expression here with this dot product, in the problem that we're addressing, the electric field at point P is only going to be in the z direction, as we've already seen, for example, back in chapter 21 with our Coulomb's law calculation. So then therefore, let me rewrite the dot product here on the right-hand side of the expression in the following way. Like so, where we're specifically describing the electric field in the z direction here at point P. So now let me go ahead and take the negative sign in the dz and move it to the other side and solve for the electric field. And that then gives us the following. So what I have to do with the expression on the bottom board is essentially differentiate it with respect to the z direction tack in a negative sign, and that then gives me the magnitude of the electric field in the z direction at point P. Now, prior to doing that, however, on the bottom board, we actually have already seen a version of this expression before. We saw it back in chapter 8, back in our unit on work and energy, at the end of the chapter, or the end of the unit rather, when we were talking about potential energy diagrams. So recall the following. Okay, change in potential energy is equal to the work done against the conservative force. That's equal to the negative of the work by the conservative force, like so. Okay, let's get rid of the integral sign. So infinitesimal change in potential energy equals this. Okay, let's say that the force is only a function of small r, so then therefore this. And then move the negative sign and the dr to the other side. And then therefore the conservative force's value is equal to the following expression. And then we saw this on a potential energy diagram as the negative of the slope of a line tangent to the curve, describing the potential energy as a function of r. This is essentially the same thing, except all that we're doing here is dividing out by the positive test charge q that would be placed at this location. So then therefore, instead of the electric force, you then end up with the electric field, and then instead of change in potential energy, you end up with change in potential. Hence the expression that I wrote down earlier to describe the electric field in the z direction. So the electric field in the z direction is equal to the negative derivative of this potential at point P in the z direction. So I have to differentiate this right here with respect to the z direction. That then gives me the electric field. So let's go ahead and do that. So let me write it like so. Here's our constants. Okay, let me put this guy that was originally in the denominator. I'm going to write it like this, like so. Okay, let's go ahead and calculate the derivatives. Let's pull the constants out in front. So then we have negative sign. Okay, and then negative 1/2 out in front. Like so. Z squared plus A squared to now the negative 3/2 power. Take the derivative of what's inside. Like so. Let's go ahead and simplify. Cancel out the negative signs. Cancel out 2. Like so. And then therefore, the electric field at point P in terms of the z direction is now the following. Q over 4 pi epsilon naught. And then we have here then 1 over this quantity, times z rather. And then 1 over this quantity. There we go. Like so. Okay, now back in chapter 21, when we did the Coulomb's law calculation, keep in mind that that was done in terms of the constant small k, which is the 1 over 4 pi epsilon naught here in front of the expression. So here's how we saw it as the answer back in chapter 21 as a vector. We saw it as kqz over z squared plus a squared to the 3/2 power in the k-hat direction. So if necessary, go back in your notes and just observe or check that calculation that we did for the ring of charge back in chapter 21. You'll notice that it's exactly this value here. So then therefore, you're kind of left with a question. Should you encounter the ring problem, for example, on an exam in some manner? What's the easiest way to calculate the electric field? The brute force calculation that we did back in chapter 21, where we set up the integral for Coulomb's law, or actually this method right here, where you find the potential at point P first, and then just take a derivative and tack in a negative sign in order to arrive at the electric field's magnitude in the z direction.